Hello everyone, we are Group B and today we will be presenting our artificial neural network mini project for the BAXI 3133 supervised by the Professor T.S. Dr. Burhanuddin. The title of our project is Pneumonia Detection from Chest X-ray Images using the Transfer Learning with CNN. Our group consists of 4 members which are Chi Fang Yi, Lim Jiahui, Yong Qing Han and Wong Man Yi. For this presentation, I will be covering the introduction, abstract and data description section of the project. The abstract of our project is pneumonia is a serious respiratory disease that affects millions of people worldwide. If it is not detected early, it can lead to several health complications. Therefore, this project aims to develop a deep learning model that can automatically classify the chest X-ray images into the 2 categories which are normal and pneumonia. By using the transfer learning, the project demonstrates that the deep learning can support the medical image classification. At the same time, explainable AI also important because it helps us to understand how the model makes its predictions. The introduction of our project is the pneumonia is a respiratory infection that causes the inflammation in the air sacs of one or both lungs. It is a serious health issue, especially for the children and the elderly patients. Chest X-ray images are commonly used to detect the pneumonia. However, manually interpretation by medical professionals can be time-consuming and may affected by the human error. With the recent advances in artificial intelligence and deep learning, automated disease detection system can help support the medical diagnosis. In this project, we developed a binary classification system using the transfer learning to classify the chest X-ray images as either the normal or pneumonia. We selected the efficient net B0 because it provides a strong features extraction while remaining the computationally efficient. For the dataset used in this project is the chest X-ray pneumonia dataset from Kaggle. The dataset contains 2 classes which are normal and pneumonia. Therefore, we combine the original training and validation dataset and perform a stratified 80 to 20 resplit. As shown in the table, the final dataset contains the 4185 training images, 1047 validation images, and 624 testing images, giving a total of 5856 images. The training set contains 3106 pneumonia images and 1079 normal images.
Hi, my name is Humani. Next, I will explain the development environment, tools, and deep learning concept used in our project. For this project, we develop and train our model using Google Colab Laboratory, also known as Google Colab. Google Colab is a cloud-based Python development platform that allows users to run machine learning and deep learning applications directly through a web browser. To access Google Colab, simply open a web browser and search for Google Colab. Sign in with your Google account, then go to File, Notebook. This creates a brand new Python notebook environment where we can start coding immediately. It's quick, simple, and ready to use. Since deep learning requires a lot of computational power, so we enable GPU acceleration in Colab. First, select runtime, then change runtime type. Second, choose default GPU, then save. Now the notebook will use GPU acceleration. Finally, verify by running a short TensorFlow command to check if the GPU is active. This step ensures our training process runs much faster compared to using just a CPU. Although Colab comes with many libraries pre-installed, sometimes we need additional package. For example, we can install Kaggle Hub using pip install -q Kaggle Hub. Other essentials libraries include TensorFlow, NumPy, Pandas, Matplotlib, and Seaborns. This library provides the tools we need for data handling, visualization, and building deep learning models. After that, before building our model, we import the necessary deep learning libraries. From TensorFlow, we bring in modulus for constructing neural network. For scikit-learn, we import function for slipping dataset, evaluating model, and handling class imbalance. Together, this library gives us the functionality to design, train, and evaluate our deep learning model effectively. Finally, we download the dataset. For this project, we use the chest X-ray pneumonia dataset from Kaggle. Using Kaggle Hub, we can download it directly into Colab with just a few lines of code. The dataset is automatically stored in the working directory and organized into train, validation, and test folder. This structure makes it easy to pre-process the data and train our model following best practices. With the dataset downloaded and organized, we can now move on the deep learning approach we use. Now that we have set out our environment and downloaded the dataset, let's talk about the deep learning approach we use in this project. Deep learning is a subset of machine learning that uses artificial neural network to automatically learn patterns from data. In our project, we use Python together with TensorFlow and Keras to develop a CNN model based on efficient net B0. The advantage of deep learning is that it can automatically extract important image features without requiring manual features engineering. This allows the model to classify chest X-ray image into normal and pneumonia categories. Now that we understand the model concept, let's look how we prepare the data before training. Before training the model, several pre-processing techniques were applied. First, all images will resize to 224 by 224 pixels to match the input requirement of efficient net B0. Next, data augmentation techniques such as rotation, zooming, translation, and brightness adjustment were used in increased data diversity and reduce overfitting. We also discovered that the dataset contained more pneumonia image than normal image. Therefore, class weight we apply during training to reduce bias toward the majority class. With the dataset clean, balanced, and ready, we can now move to building and training our CNN model.
My name is Chi Fang Yi. Now I'm going to talk about the model architecture and training for our system. When looking at our architecture, we decide to use transfer learning approach using efficiency net B0. This pre-trained model has learned rich image features from the ImageNet dataset, such as edges, textures, and lighting gradients that can be applied to X-ray features. For feature extraction, the base layers of efficiency net is frozen, means that we don't retrain these convolutional filters. We just reuse them as rich feature extractor learned from millions of ImageNet images. Next, we remove the original classification layer, which predicts thousands of different categories, for example, dog or cat, and replace with a custom head design for binary classification. The custom head to adapt ImageNet features for pneumonia detection contain these three layers. The first layer is global average polling 2D. It helps to compress the feature maps into a single vector. It reduces the tensor shape and drastically reduces the number of parameters and makes features translation invariant. Translation invariant means that the model can recognize an object even when its appearance varies in some way. The second layer is dropout layer. During each training step, 30% of the neurons in these layers are randomly set to 0. This is to prevent overfitting by force the network to not rely too heavily on one neuron. The third layer is dense output layer. This final layer consists of a single neuron. It utilizes the sigmoid activation function to squeeze the model's raw output score into a decimal value strictly between 0 and 1, representing the probability that the given chest X-ray indicates pneumonia. Next part is training configurations and optimization pipeline. The loss function we use is binary cross entropy. This is the standard loss function for predicting a 0 or 1 outcome. It measures the performance of a classification model whose output is a probability value between 0 and 1. For optimizer, Adam is used with initialized learning rate of 0.001. There is also class imbalance occurring in our dataset. A standard model may get biased toward the majority class because predicting the majority more often gives higher accuracy. To correct this, class weights are computed and passed into the training loop. We can see that the weight for normal class is almost 3 times higher than pneumonia. This means that during training, mistake on normal images will receive higher penalty compared to mistake on pneumonia class. Lastly, to protect against overfitting and optimizing training time, our pipeline utilizes early stopping callback. If validation accuracy doesn't improve for 5 consecutive epochs, training will stop early. After stopping, the model will automatically save the absolute best version of the model during training.
My name is Lim Jiahui, and I will present finding and result. This slide shows the training performance of the efficient net B0 model. The loss decreased throughout the training, while the AUC increased consistently from approximately 0.91 to over 0.99. The training and validation curve remain relatively close, indicating it has a good generalization performance and no self-overfitting. The model learned meaningful features from the chase X-ray images and achieved a stable conversion. Next, for this slide, present the final evaluation result of the proposed model. The ROC curve shows the model ability to distinguish between the normal and pneumonia chase X-ray images across a different classification threshold. The model achieved an AUC score of 0.952 that showing it had a strong discrimination between the normal and pneumonia cases. For the confusion matrix, it showed that 370 out of 390 pneumonia cases were correctly detected, resulting in a recall of 95%. Overall, the model achieved 88% of accuracy, 87% of precision, and 91% of F1 score, although the precision is slightly lower, but the high recall is desirable in medical screening because it minimizes missed pneumonia cases. In this slide, show how we use the GRAD CAM to understand the model decision-making process. On the left, we have a false negative case. The patient actually have pneumonia, but the model incorrectly predicted as normal with 57.7% of confidence. From the GRAD CAM heat map, we can see that the part of model attention is focused on the R orientation marker instead of the lung region. This suggests evidence of shortcut learning, where the model relies on dataset artifact rather than purely medical feature. On the right-hand side, we have a correct prediction. The model correctly identified pneumonia with 99.71% of confidence, and the heat map clearly focused on the lung abnormality. This indicates that the model using clinically meaningful information to make its decision. The GRAD CAM helped us verify not only whether the model was correct, but also whether it was correct for the right reason. This demonstrates that high accuracy alone is not sufficient. Expandable AI is essential for trustworthy medical AI system. Despite achieving a strong performance, there also have several limitations. For the efficient NetB0 was used only as a frozen feature extractor, and the future work could include that the fine-tuning selected layer. For the GRAD CAM revealed that the model occasionally rely on image marker such as a letter R and the letter L instead of the lung abnormality. To address this issue, future work could apply the UNet lung segmentation or the OCR-based marker remover. In addition, also can using a large multiple hospital dataset could further improve the model robustness and generalization. In conclusion, for this project, our group has successfully developed a pneumonia detection system by using a transfer learning with efficient NetB0. The final model achieved 88% of test accuracy, 87% of precision, 95% of recall, and the AUC score of 0.952. The high recall is particularly important because it allowed the model to correctly identify the most pneumonia cases while minimizing misdiagnosis. For the GRAD CAM visualization also provide a valuable insight into the model decision-making process and help identify the potential shortcut learning behavior. Overall, the project demonstrates the effectiveness of deep learning and the expandable AI for assisting the pneumonia screening from chest X-ray images.
To wrap up our presentation, we want to proactively address a Q&A section. The question is, how does applying random rotations, zooms, and brightness adjustment in data argumentation help if a real-world clinical X-ray is usually taken from a fixed, straight angle? And our answer will be, while clinical X-ray aim to be standardized, real-world conditions vary slightly. Patients might tilt their chest, breathe differently, causing a shift, or different X-ray machines might output slightly varied lighting contrast. By artificially creating these variations through data argumentation, we prevent our network from memorizing the specific orientation or lighting of our training images. This forces the model to learn the actual underlying biological patterns of pneumonia, thus improving its overall robustness. That concludes our presentation on deep learning for pneumonia detection. Thank you to Professor Burhanuddin and our viewers for watching.